everyone. Thank you for joining us tonight. This is our May 2022 presentation for the Naperville Astronomical Association. Okay, so tonight's presentation. If you have questions and you're watching on Facebook, you can post those in the comment section, and Chris will forward those to our speaker. Or if you're watching online, or if you just want to email your question, you can email questions@naperastro.org. Those will go to Chris, and he'll feed those to our speaker as well. Tonight, our speaker is Brian Welch. Brian recently got his Ph.D. in astronomy and astrophysics at Johns Hopkins University. Congratulations! He literally just defended that a couple weeks ago, and he will start very shortly at his new job as an astrophysicist at NASA Goddard Space Flight Center. So very impressive there. Brian's going to be talking to us tonight about finding the first stars with the James Webb Space Telescope. So Brian, we're going to turn everything over to you.
All right, thank you very much. Let's see, can I go ahead and share my screen here? Okay. Cool. So hopefully you can see my slides up now. So yeah, like you said, I just finished up my PhD at Hopkins, and I will be starting up at the NASA Goddard Space Flight Center later this summer, and really just focusing on new data from the James Webb Space Telescope. So tonight I'm going to talk to you about how we're going to be going about finding the first stars with the James Webb Space Telescope.
Hey, Brian, the audio is a little bit choppy from you.
Oh, okay. Let's see.
Actually, it sounds fine now. Of course, it sounds fine now, but the first little bit was choppy. We'll keep you posted.
Okay. If it, let me know if it gets too bad. I can always try to leave and rejoin. Sometimes that helps. But if not, hopefully it will. Hopefully it'll hold out for the rest of the talk. So anyway, as I was saying, I'm going to be talking about the first stars, how we're going to be able to find those with the James Webb Space Telescope. And as part of that, I'm going to be talking about a recent discovery that I made of the most distant individual star that's been found yet. So that's what you're seeing in the image on the right, just kind of to lead with the result a little bit. That little red dot that white arrow is pointing to is the most distant star. We nicknamed it Earendel, and it's far enough away that we're seeing it as it was just about 13 billion years ago. So it's within the first billion years of the universe, and it's a really exciting thing to look at, and I'll give you a bunch more details on that later on. But I'm going to start off a little bit closer to home and talk real quickly about sort of how we're able to observe stars, and how we're eventually going to be able to observe very distant stars, and what some of the challenges are. So starting off close to home, this is something that you probably all recognized from the night sky. These are the Pleiades. This is an open cluster that's pretty nearby to us. 7 of these stars are visible with the naked eye just about every night. I can even see them here in Baltimore City. So it's a nice thing that you can go up and look at whenever you want. The big thing that I want to point out here, with this being a particularly nearby star cluster, is that you can see all of these big blue stars, and you can pick them apart pretty easily. So you can tell, where one star ends and another begins, and it's pretty straightforward to pick out these individual stars. That's not always the case with a lot of the astronomical objects that we look at. Cluster. This is just a large, dense group of stars that you can still pick out individual objects here. It just gets a lot more challenging. So a lot of these stars, are very close together. They're a little bit fainter, so you see a lot of these, very close by points of light that are a lot tougher to pick out. But at this point, we can still look at individual stars, and we can also kind of start looking at the total population of the stars, in these sorts of objects. So we can say, for this globular cluster, for example, these are mostly older stars, which is why we see them looking a little bit more red. So these look a little bit more orange, whereas the Pleiades that we were looking at before are all these younger, much bluer stars. As we go a little bit further out, this is another star cluster. This one a little bit further away still. This is the R136 star cluster in the Large Magellanic Cloud. Again, you see we're going back to these blue stars. So this is a much younger object than the globular cluster that we were looking at. But you can see, especially right in the core of this particular star cluster, there are so many stars, and they're starting to get just far enough away that these stars are all kind of starting to merge together and overlap. So we can't easily see right in the core of that object. We can't easily pick apart, where one star ends and another one begins. And this is where the challenge of looking for individual stars in more distant objects really arises, is that as we start looking at these larger, brighter systems that are further away, we're looking at the light from, in this case, thousands of stars that are kind of all blended together. So then, we start going back to, like I was saying before, we're kind of looking at populations of stars to get a sense of what those individual stars might look like. And in this case, as with the Pleiades, this is all blue stars. So these are, generally very young objects. The situation gets even more challenging when we go even further out. So this is our nearest neighbor, the Andromeda galaxy. And you can see here, it's almost impossible by eye to pick out an individual star within the Andromeda galaxy in this image. Where everything is kind of smeared together. It's looking very much so blended. And this is where, to see this galaxy, we're seeing the light from billions of stars all mixed together. This one is close enough that with very powerful telescopes and lots of hard work, we can start picking out individual stars within this nearest galaxy, but it becomes a much larger challenge. And obviously by eye, it's not so easy to see. So again, we end up going back to that population analysis, where you can sort of see in the center of this galaxy, the stars are a little bit more yellow in color, indicating that they're probably a little bit older. Whereas as you go further towards the outskirts, it gets a little bit bluer. These are probably where some of the younger stars are going to be. And then, as we continue to take steps further and further back, this problem gets even more tough, even more difficult to work on. So this is the Hubble Ultra Deep Field. And this is, using the Hubble Space Telescope and getting as much data as we can. We're kind of trying to find the very most distant objects. So most of the objects that you're seeing here are distant galaxies. And you can start to see sort of the scale of the problem. Some of these little tiny point-like sources that we're seeing in this image are entire galaxies. So these are, again, billions of stars that we're seeing the light from all of them essentially collapsed into just a few pixels on the Hubble Space Telescope. So this is one of the highest resolution telescopes that we have. And so, trying to find an individual star at such a great distance becomes incredibly challenging here. So we're back to that, looking at populations of stars. So we can tell based on the colors of the galaxies that we're seeing, what sorts of stars they're forming, and what the galaxy properties are like, and then you start to infer what the properties of the star might be like. But if we really want to be able to find the first stars, it will be really important not only to find galaxies that are full of them, but also to find individual objects. And you can see that it's going to be a bit of a challenge. And just to kind of hammer this home one more time, these are a couple of the most distant galaxies that have been observed with Hubble so far. So there's one on the left that is about 400 million years after the Big Bang. And you can see this kind of reconstruction of it in the little zoom in box. And it kind of just looks like a fuzzy red blob. It's again, going to be incredibly challenging to pick out anything individual within this galaxy that's much smaller than the galaxy itself. And the same thing for the other very distant galaxy that I'm showing. This one is even slightly magnified by gravitational lensing. I'll get back to gravitational lensing a little bit more in a little bit, but you can still kind of see that, this galaxy just kind of looks like a red smudge. There's not a whole lot of detail here that we can kind of pick apart the way that there was in much closer galaxies if we look in the Milky Way, it's pretty easy to pick apart individual stars. But as we look at these most distant objects, it gets much, much more challenging. So if we want to look at the first stars, we have to kind of figure out how to start picking them apart from these very distant galaxies. So as we look at more distant objects, we're essentially looking back in time, since it takes the light from these distant objects a certain amount of time to travel across that vast distance of space and reach our telescopes. So like I mentioned, with Hubble, we're able to see galaxies that are just about 400 million years after the Big Bang. So we're getting pretty close back there. But there's still this little gap. So just sort of a real quick history of the universe. After the Big Bang, everything eventually kind of settles out and smooths over into one of the cosmic dark ages. And at this point, this is where we kind of have this sea of hydrogen gas and helium gas that are kind of, almost featureless at the beginning. But there are just sort of little ripples in the density of this gas in different spots. And over time, gravity starts pulling more and more gas towards these slightly more dense regions. And that's what actually ends up forming the very first generation of stars. So as this gas kind of collapses, it eventually reaches a point that its gravity is strong enough that it can pull it down to a point that it actually ignites fusion of hydrogen, and that turns on the very first stars. And this is something that's been completely invisible to the Hubble Space Telescope so far. After these first stars form, they kind of start to again sort of be attracted to each other, and they start to turn into the very first galaxies. One really interesting thing about these very first stars too is that they formed out of just this primordial mixture of hydrogen and helium. So stars that we see today will have a lot more heavier elements. You'll get anything astronomers refer to as metals, which is anything that's heavier than helium. So you get a lot of carbon, oxygen, these sort of other heavier elements that form in the cores of stars, and then eventually, as later generations of stars form, they sort of form out of more of these metals. But the very first stars would have had none of these, which makes them particularly unique and particularly interesting to look for. So not just are we looking for the first stars just for fun, but it's really giving us a way of sort of figuring out where everything else in the universe that we know of came from, because it all kind of started with these very first stars. But like I said, it's a very difficult challenge, and the Hubble Space Telescope is an incredible instrument, but it wasn't really designed to be able to look for things that are this far away. These first stars would have formed only about 100 million years after the Big Bang. So we really need a new instrument to be able to give us this sort of information. And the reason that the Hubble Space Telescope is kind of limited here is because, like I said, it was designed for something else. So it was designed to look at light that's kind of in the near infrared to near ultraviolet wavelengths, which is where most of the light that we see in the universe actually tends to reside, especially in nearby galaxies, nearby objects. Most of the detail that we need is in those wavelengths. But to look at these very, very distant objects, it actually, as the light from these most distant objects crosses space is expanding the whole time. So the universe is constantly expanding. And as this light crosses this expanding space, it actually stretches out the wavelength of the light. So, a photon that was emitted in the ultraviolet in a very, very distant galaxy, as it travels across space towards us, it'll get stretched until it eventually reaches the visible spectrum. And then, as it travels more and more, it gets stretched even more into the infrared. So the Hubble Space Telescope has this limit of, about 400 million years after the Big Bang. And at points beyond that, things are just redshifted too much. So they're shifted too much into the infrared. So the instruments on the Hubble Space Telescope can't actually see these objects anymore. Luckily, we do have a new telescope that you may have heard of. It's called the James Webb Space Telescope. And this is something that was sort of purpose-built in part for this kind of science. So it's got that infrared capability, so it can really see these most distant objects. So I'm gonna talk a little bit now about the James Webb Space Telescope. and how it's working and what it's going to be doing.
And
All right,
maybe
I am back in. Hopefully the audio is a little bit better this time around.
starting off better. Matter of fact, we can test it out while you're answering the question. How's that?
Okay, yeah, that sounds good.
Okay, so Eric Clays asked, were you a lead author on the paper about the farthest star?
Yes, yeah, I am the lead author on that paper.
Okay, and the audio does sound better, so hopefully we can keep driving forward with that.
Okay, awesome. I will go ahead and try to share my screen again here.
Oh, and if you don't have any other apps running too, make sure that there's no other apps running just in case that's what's causing the issue.
Yeah, all I've got running is the Zoom and then the talk. So
okay, yeah, just double check.
All right, is it did the screen share go through effectively? Is it slide back up?
Not yet, no.
Okay. All right, how about now? Is it?
Yes.
Cool. Okay, so hopefully the audio holds out this time. So as I was saying, just kind of going to go now into a quick comparison of the Hubble telescope and the Webb telescope, just to kind of get a sense of how Webb is going to give us this extra boost in terms of seeing some of these most distant objects. The first thing that really stands out is just the size of the primary mirror of the telescope. So the Hubble Space Telescope primary mirror was about 2.4 meters in diameter. So it's a big telescope, but it's kind of nothing compared to the Webb telescope, which is a diameter on its primary mirror of about 6.5 meters. This little hexagon shape honeycomb structure that you see in the Webb mirror is mostly due to the fact that to get something this big into space, it actually had to be able to fold up. And I'll show you in a minute how the telescope actually was able to unfold once it got into space. It's a really cool process. But this giant mirror gives us sort of two advantages. The first is that with an increased mirror size, you get better resolution. So something that's a larger diameter is able to pick apart small features in distant objects more easily than something with a smaller mirror. The other thing is these very distant objects are also very faint. So this much larger mirror gives us a chance to collect more of that incoming light. It's sort of, you can think of a telescope as like a light bucket, and the bigger the bucket, the more light you collect and the easier it is to see these distant objects. So with this new Webb Space Telescope, the giant mirror is going to give us a huge advantage in just the amount of light that we can collect, and therefore the sort of objects that we'll be able to see in the distant universe. The other thing that's very different this time around is, like I mentioned, the Webb Space Telescope is designed to look into the infrared, whereas Hubble was designed to look at sort of the near ultraviolet through the near infrared. So sort of that visible and just beyond visible light that we would normally see. The biggest thing that this gives us in terms of looking for very distant objects is, like I said, we're able to see things at much higher redshift. So we're able to see these much more distant objects that have had their light stretched out even more as they're crossing these vast distances across the universe. So this gives us sort of a new window into what this very early time in the universe is going to look like that we just, we couldn't quite get with Hubble. It was just kind of just beyond the limit of what we could get with the Hubble Space Telescope. So it's going to be really exciting to actually see, what this new telescope is going to be capable of. So the telescope has launched. Just kind of a quick update on where it is. It launched back in December on Christmas Day. It was a wonderful Christmas present for all of the astronomers. This is actually a photo that I'm showing that I took of my computer screen as I was watching the launch on Christmas morning. It was a fun time watching that. It's kind of the Christmas morning present for anyone who's been involved with this. It was a good time. After the telescope launched, the launch went incredibly well. This was kind of the last picture that we were able to get of the Webb Space Telescope after it had launched. So this, what you're seeing here is the actual telescope itself having just separated from the final stage of the rocket booster that it was on. And you can see it just kind of floating with Earth back there in the background. This was an incredibly fun sight to see. This was something that I think everyone in the community was really excited about, knowing that this had launched. But it was kind of just the first step. So like I said, the Webb telescope had to fold up into a small configuration to be able to fit into the rocket. And so hopefully this will not cause too many problems if I try to play this video here. So this is just going to be a quick little demonstration of the actual unfolding process. So, this is a really giant instrument. So it started up in this fully folded up configuration. And then you can kind of see the different steps of the unfolding kind of playing out here after it launched. And this is really the big one here that you're about to see is the unfolding of this sun shield. So this sun shield that is unfolding now on the video is about the size of a tennis court. It's made up of 5 independent layers of incredibly thin material that's meant to basically block heat from the sun and keep it away from the instruments of the telescope that have to be kept at a very cold temperature to be able to see this infrared light. And getting this all to deploy was a huge feat of engineering. There were hundreds of release mechanisms and all sorts of pieces that had to all work. And with all the testing that they did, amazingly, this all worked perfectly, which was absolutely incredible. But this was definitely the most nerve-wracking few weeks for all of the astronomers that were working on this. So once that sun shield finally gets deployed, you can see those arms extend and put that secondary mirror out in front of the telescope. And then these wings of these hexagonal mirrors all unfold into this final configuration. So now that's where you get that full 6 meter or 6.5 meter mirror. Then eventually it gets out to its very distant orbit. So the telescope is in orbit around a point called Lagrange point 2, which puts it sort of co-orbiting the sun with the Earth. So it's sort of way out there in space to help give it the most stable position to keep all of the instruments in their right configuration. So obviously getting this whole thing unfolded was a huge challenge. Luckily we had a lot of great people working on it to make it all go very smoothly. No, I don't want to play this again. Okay, there we go.
Brian, I do have a couple questions I could throw your way right now. So
yeah, sure.
Okay. So Bill Perdue asks, does the wavelength of light being studied have any practical requirements on the optical quality of the mirrors themselves, perhaps a bit more forgiving?
Yeah, so if I understand correctly, you're asking about the optics of the mirror that are going to be required to be able to observe the far infrared or the infrared wavelengths that we're looking at. So I mean, obviously one of the biggest requirements is you have to have a material that will effectively reflect those infrared wavelengths, which is why the mirror actually is golden like that. So that gold reflects those infrared photons really effectively. And so that's this mirror coating that we have that helps to get the most out of this telescope. And then besides that, to be able to look in the infrared, we need to have instruments that are going to be kept very cold. So infrared light is it's the same thing that produces heat that we feel as heat here on Earth. So our bodies glow in the infrared, which is why if you ever see those thermal cameras, those are just infrared detectors. But to be able to look at objects in space in the infrared, you have to have a detector that is not warmer than the thing you're looking at. So we have to be able to keep those detectors very cold. And that was another one of the technical challenges in designing the Webb telescope. And that's why we have that big sun shield that blocks all of the incoming light and the incoming heat from the sun to be able to keep all of those telescope elements nice and cold so that we can see all of that infrared light. Were there any more questions?
Yeah, there was, but I think you just answered it. So, and the person asked it said, yes, you did. So, okay.
Awesome. Okay, awesome. So the next thing I'm just gonna go over here is the performance of the telescope now. So it all unfolded very well. It made it to its orbit out at L2, and it's all unfolded and set up. And this was one of the first images that we got back when the telescope had actually all finally been aligned. And this was an incredibly exciting time to actually get to see the sort of first image. So, you know, with all these different hexagonal plates that make up the main mirror, it was a big challenge to actually get all of that focused and get that all focused remotely. So each of these mirrors actually originally produces a different image. So it kind of shows up in a different place on your detector. And you have to tweak each mirror individually until eventually all of those images line up right on top of each other. That was quite a challenging process, but all of the people working on it had really practiced it a lot and had sort of gotten it down to about as precise as they could possibly do. And eventually that all was rewarded into this first focused image that we have. So this is just a bright star that's nearby, and you know the most exciting thing here is just to see how crisp this image came out after that first alignment and initial focusing. And you can even start to see, you know, all of the background objects here. This was looking at this was already, you know, getting people excited for the kinds of things that Webb is going to be capable of doing. Since then, the biggest process next has been aligning each of the individual detectors, and that just recently completed. So now we have all of the detectors are aligned and focused. They're producing these nice crystal clear images. So all of these are just images of sort of nearby stars and nearby star clusters, just to kind of give, you know, plenty of bright sources for the telescope to pick up. And, you know, you can really see just how sharp a lot of these images are. These are really beautiful to see right off the bat. One of the things that I most want to highlight here, this is something that I've seen a few people do. This is a comparison now of different infrared space telescopes. So on the far left here was the WISE telescope. That's the Wide Field Infrared Survey Experiment. And you know, this was a 0.4 meter mirror, so it was a much smaller telescope. And you can see, you know, just how fuzzy of an image that gives you. The next step up is the Spitzer Space Telescope, which is kind of our infrared workhorse over the last you know, few years for sure. This one had a 0.85 meter mirror, so a little bit bigger, gives you a little bit more clarity, but it, you know, it's still, these are stars that we're looking at and they're still pretty fuzzy to see. So still a lot of work left to do after Spitzer. But now we're getting this JWST image that I'm showing here on the right. And you can just see the clarity is miles better. We can see these stars, you know, perfectly clearly. We can see so much more detail of this gas structure, this dust structure that's coming around these stars. And you can see so many more objects in the background too. You know, you could kind of tell that there were maybe a few background sources in the Spitzer image, but now with this Webb image, you know, you can just, it kind of gives everybody a little taste of just how powerful this telescope is really going to be. You know, these were pretty quick observations just to make sure that the alignment was all set. And we're already, you know, far surpassing anything that we had in the infrared before. So this is a hugely exciting thing to see, and it's just really bodes well for just how powerful this telescope is going to be. It's going to be really cool to actually get the first science data off of this.
Brian?
So, you know, what is this actually going to give us now? Going back to this slide that I was showing earlier, you can kind of
Brian,
see that.
excuse me.
Yep.
I'm sorry. Sorry, I didn't mean to interrupt. Trying to catch you a little second ago. We got a request. Can you click the hide button on the sharing bar? It's showing up on
Oh,
the
yeah.
screen.
Sorry, I didn't realize that was being shared as well.
Yeah, not a problem.
Okay, so that should be gone now. Yeah, sorry about that.
Yeah, and we did have another question kind of before you go much deeper into this topic. Eric Clays asks, did anything not go well during the deployment part? I think he tried to get that question in earlier, and I must have missed it.
Pretty much everything went according to plan or better. So, you know, obviously nothing is perfect, but they didn't plan on anything being perfect. But, you know, sort of our best estimates were still exceeded by what we were actually able to do with the full deployment. So, you know, everything went about as smooth as it possibly could. We didn't have any hiccups with deploying the telescope or getting it aligned. and even down to the launch of the rocket, we actually the initial launch from Earth to when the separation from the main booster happened went better than expected, meaning that the telescope has more fuel than we expected it to have, so it'll have a longer lifetime out there. So everything has gone according to plan or better for the most part. All right. If there are no other questions at this point, I'm going to jump ahead now and just kind of point out that with these incredible images that we're seeing, we're very confident that Webb really is going to get us back to the very first galaxies and get us sort of a glimpse of what these things are going to look like. These most distant objects, we have the telescope that we need to see these first galaxies and really sort of push past those limits that we ran into with Hubble. So it's going to be a very exciting time to study these very distant objects with Webb. But I do want to point out, what about the first stars? Those very first generation stars are something that are going to be, really interesting to look at. Like I said, they're going to have formed just out of this hydrogen and helium. So they're going to look a lot different than the normal stars that we see in the Milky Way and other nearby galaxies. And unfortunately, without any assistance, Webb won't be able to directly observe individual first generation stars. Despite these stars being, fairly large and fairly bright, they're just not quite bright enough for Webb to be able to see them directly, which is, unfortunate. But luckily, we have a solution and we have a way around that. And that is to use massive galaxy clusters in the foreground as sort of cosmic telescopes. So this is with a phenomenon that's known as gravitational lensing. So in Einstein's theory of general relativity, massive objects actually distort the space around them. And in this case, what I'm showing here in this image, you can kind of see this grid. You can kind of think of it like a sheet on the ground. This is meant to represent space. And then you have this massive galaxy cluster between Earth and a distant galaxy. And that actually is bending this space and kind of making this little divot. You can kind of think of this as like if you were standing on the bed of a trampoline, for example. If you have a person standing on a trampoline, they make a little divot in the bed of the trampoline. And as you have a larger, heavier person, they make a bigger divot. A smaller person makes a smaller divot. It's the same thing in general relativity with mass bending space. One of the most interesting things to come out of this too is that when light travels through this bent space, it actually seems like the light itself is bending around these distant objects. So you can kind of see, with those two highlighted orange rays coming out of this distant galaxy, light can actually pass around this massive object and kind of bend through it, just like if it were going through a glass lens. This tends to produce multiple images of the background galaxy, since they kind of take two different paths around the cluster to still come back to our telescopes on Earth. And one of the most important features of this is that it gives us a much higher resolution than what would be possible with a telescope on its own. So these background galaxies, just like looking through a magnifying glass, they appear magnified. And so, this is kind of just a fun little animation that kind of gives you a sense of what this might look like. Here we just have a dark mass kind of moving across a field of background galaxies. And you can see, it produces these images of these background galaxies that are, stretched out and elongated into these big arcs. At times for this particular setup, they even, form these full, what are called Einstein rings all the way around the mass. And it really gives us a huge boost in being able to see these things. They appear much bigger and much brighter than they would if we didn't have this effect. Here's what this looks like for galaxy clusters in the real world that are actually lensing these background objects. So all of those long arcs that you can see in these various images are background galaxies that are gravitationally lensed. So they're stretched out, they're magnified. We're seeing them, much larger and much brighter than we would without these galaxy clusters being there. And sometimes they even form fun little shapes like the smiley face that I put on the right. I love throwing that into various talks just because I think it's a very fun little thing to have a smiley face in space. So this is what this actually looks like. And like I said, one of the big effects here is that this actually magnifies these background galaxies. So this is an example of a lensed galaxy. You can see on the far left, this is the image that we actually took with the Hubble Space Telescope. So this image, you see, these three different segments of this galaxy. Those are three multiple images of the same background galaxy that have just kind of taken those different paths around the galaxy cluster to form these three images that are all kind of connected in this long arc. Using a variety of models and techniques, we're able to actually reconstruct what this galaxy would look like if it were not gravitationally lensed. And that's what gives you this panel sort of in the middle left here. This is that source reconstruction. And what you can see is there's all this small scale structure. These are small star clusters in this galaxy. And really what this gives us is a huge boost in the small scale objects that we can see in these distant galaxies. And just for fun, those two panels on the right are what this galaxy would look like if we didn't have that lensing effect. So with the Hubble Space Telescope on sort of the right middle, it would look kind of just like a blob. We lose all of that information of these really small scale objects within this galaxy. And even with the James Webb Space Telescope, we gain back a little bit of that with the bigger mirror. It gives us a slightly higher resolution, and it can give us a little bit more of that substructure, but it kind of pales in comparison to what we could get with lensing. And in this particular case, we would need about a 35-meter telescope in space. So Webb is 6.5 meters, and we already had to fold it up and come up with all sorts of engineering shenanigans to make it work. And getting a 35-meter telescope in space is something that would be a much greater technological challenge. So using gravitational lensing really gives us a huge boost in this regard to be able to find these small details in distant objects. In some cases, this is even enough to actually boost individual stars to the point that we can pick out just one star amongst a distant galaxy. So this is one of the first individual gravitationally lensed stars that was discovered. And what you can see, in the big image in the middle, you've got the multiple images of the source galaxy, and then that white dashed line is it's a point where the magnification from the gravitational lens kind of diverges. So it's sort of like an asymptotic curve where as you get closer to that line, the magnification increases dramatically. And realistically, there's a limit on just how highly magnified a thing can be. But if you have a small source that's really close to that line, you can get a really incredibly high magnification. And that was what happened with this particular star in this galaxy. It was actually discovered when the brightness of the star temporarily fluctuated as it was moving across the different features of the gravitational lens. It temporarily went to a slightly higher magnification, which enabled us to actually, it enabled this team to actually pick out what the star was, as opposed to just thinking, oh, this is some other component of this galaxy. But you can see in those two black and white images on the right, where that blue arrow points, that's where the star actually is. So it's kind of there in the first image. It's kind of faint, and you might not look at it and think that it's a star. But then in that second image, it gets brighter. And that's something that you would only expect to see if you had a very compact source, something like a star within this distant galaxy that was lensed. There have been a few other discoveries as well. All of them have kind of relied on that same technique of a star that was temporarily boosted by this magnification effect. And you can just kind of see, where all these different lens stars are. Some of these were actually all lensed in galaxies lensed by the same galaxy cluster. So there's really sort of a lot of area to explore with this now that we kind of know how to look for these lens stars. So all of these kind of set the stage for the idea that we can actually pick out individual stars at these very great distances. But even these stars were, although they're very distant, this was the previous record holder, and this was at just about 9 billion years into the past. So it's very distant in this very distant galaxy, but It's still, relatively speaking, it's not as distant nearly as sort of the most distant galaxies that we're looking for. So now I'm kind of going to get into how we actually were able to discover the most distant star that we've seen to date. And it started with basically an image like this. This is the much more cleaned up version of it that we eventually created. But this is the image that we got from the Hubble Space Telescope, looking for more gravitationally lensed galaxies. We weren't really looking for an individual star here. But with this particular image, what we noticed is down at the bottom of this image, you've got that long red arc. And that kind of caught our eye because anytime you have a really long arc like this, that means that you've got a pretty highly magnified galaxy. So that looked like it was something that was worth looking into. So then, I'll just kind of show a zoom in here. As we looked at this more and more, it became pretty clear that this galaxy was, not only a very long arc, but it was in the very distant universe. We were able to measure that it was within the first billion years of the universe. So the whole galaxy is at a very great distance. That's why it appears red in this image, because that light is shifted entirely to those redder wavelengths all the way out. This is all the way out within the first billion years of the universe. And eventually what we were able to find was that as we kept modeling what this galaxy looked like, as I kept kind of creating different versions of what the magnification effect from the foreground galaxy cluster would be, it kept showing this one point that arrow is pointing to had to be predicted to be at an extremely high magnification. So this sort of was what first led us to the idea that this might be something that's incredibly interesting. Not just a very highly magnified distant galaxy, which would be interesting for astronomy's sake, but this was something that was extremely magnified that could be much more interesting to many more people, besides just the few astronomers who really focus on this sort of thing. So as we dug more and more into this, it became even more clear that this one object really was at an extreme magnification. So that yellow dashed line that you have there, that is, again, that's sort of that point where the magnification from this foreground galaxy cluster starts to diverge. And that's where, if you have something that's kind of right on top of that line, that's where you're going to get these most extreme magnifications. And what you can kind of see is that line really crosses right over that one red point within the arc. So when I actually went through and calculated, in detail what the magnification would be, I found using, all sorts of different methods that the magnification for this particular point had to be greater than 1,000 times. So we're seeing it 1,000 times larger and 1,000 times brighter than we otherwise would if we didn't have this magnification effect. And I was able to work out, based on that magnification estimate, that this object has to be something that's, if it's magnified 1,000 times and it's still not resolved by the Hubble Space Telescope, it looks like, it still looks like this little tiny point of light. The only way that could be the case is if it was something much, much smaller than a cluster of stars. So much, much smaller than any star cluster that we know of from observations of nearby galaxies, of the Milky Way and our nearest neighbors, of observations of very distant galaxies. We haven't found anything nearly as small as what this would have to be. And even in simulations of galaxies across any range of time, we haven't found star clusters that would be able to fit within the region that this would have to fit entirely into to still produce this kind of point source. So that was, once we had the proof that this was actually a star, I got to pick out the name, which was pretty fun. So I went with the nickname that is Earendel. It's an Old English word that means the morning star. So this is a time period when, within that first billion years, is kind of a time period that we often refer to as cosmic dawn. It's kind of when, I thought that name was a pretty good fit there.
Brian, we lost you for about 10 seconds. You were talking about the name, how you named it, and then we lost just a few seconds of you.
Okay, sorry about that. Can you hear me now? Is everything back in order?
Yeah, everything's fine right now.
Okay, cool. Hopefully it doesn't drop again. So anyway, I was just saying that, this is we're seeing this galaxy within the first billion years. So it's kind of a time period that we often refer to as cosmic dawn. It's kind of when the lights are turning on in the universe. Everything is just kind of starting to form. These stars are just starting to form. These galaxies are just starting to form. So that morning star theme kind of fit in pretty well with this very distant galaxy at cosmic dawn. So once we had the star identified, just saying, hey, look, this is a star is pretty cool, but it's not the only thing we want to do. We want to get a sense of what the star actually looks like. So to do that, we tried to put it onto, this is what's called the Hertzsprung-Russell diagram. So I have kind of the cartoon of it on the left side here. This is what you might have seen in an astronomy textbook, or if you've taken any sort of class on astronomy or how stars form. And this is just kind of a way of figuring out what different types of stars actually are. So it's a plot of temperature on the horizontal axis and luminosity on the vertical axis. And the sun is, sort of right in the middle at the luminosity is in solar units. So how many times brighter or fainter than the sun is it? And then, you can kind of see the sun. If you squint, it's kind of right in the middle of that plot right there. And so we wanted to get a sense of, where Earendel sits within this diagram. And so that's what I'm showing on the right. So what we have, that green band is from our various models of, what the magnification of the star could be. We kind of were able to get a sense of what the luminosity would be as a function of the temperature based on the observations that we have. And basically what we found is that when we compare that to models of stars, it's most consistent with being a star that is greater than 50 times the mass of the sun. So you can kind of see over on that right-hand plot, you've got, that brown line, that 55 solar mass line is kind of the one that, spends enough time within the green region that matches our constraints that it could reasonably exist there. Whereas, that if you go down to 40, it just barely crosses in, and that's kind of just a blip in a star's lifetime that makes it really unlikely that we would actually be seeing that. So we kind of estimate that it has to be at least about 50 times the mass of the sun. And then the brightness is what you see on the vertical axis, and that's about 10 to the power 6 times brighter than the sun. So it's at least 1 million times brighter than the sun. So it's a very large, very massive star. Some sort of, some of the on par with some of the largest and most massive and brightest stars that we see in the Milky Way and in the nearby galaxies that we have. So it's a pretty interesting object for that reason. It could obviously be even brighter, potentially up to 500 solar masses according to these particular models. That gets a little bit more challenging because those extremely massive stars have incredibly short lifetimes. They may only live for 1 million years. So, finding something like that gets a little bit less likely. But, it is possible, and it's something that we're going to continue to look into because we have this kind of broad constraint at this point from what we have with Hubble, but we want to get a much better understanding of what this star actually looks like. And this is something that the James Webb Space Telescope is going to do. So with this particular star, we do have Webb observations scheduled for the first year. So we're actually, we just got the schedule pretty recently, and we're going to be able to get the very first observations of this sort of in the late summer. So it's going to be really exciting to actually finally get a chance to work on Webb data and finally get a chance to study this star in a little bit more detail. And I'm just kind of showing here on the right a comparison of the constraint we were able to put on this plot with Hubble as opposed to what we're going to be able to see with Webb. So really the biggest point that I want to hammer home here is that these Webb observations are going to really actually precisely measure the temperature as opposed to saying it could be a lot of things. And it's really going to shrink the uncertainty on the brightness of the star. So we'll be able to say, in this particular assumption, we might be able to say this is a 100 times the mass of the star or 100 times the mass of the sun. And we'll be able to say exactly what type of star it is. This is in this case, this would be something like an O star. So it's going to be a really exciting thing to see. And then in the future, as we continue to look at this star with Webb in years to come and with other telescopes, we'll be able to actually start picking apart what the more detailed properties of the star will be. So we'll start to, most interestingly, we'll start to pick apart its composition and start to look at how many of those metals that I was mentioning before does it actually have. Is this something that's, incredibly dominated by hydrogen and helium, sort of like we would expect the very first generations of stars to be? Does it have sort of a very small metal abundance, like maybe a second generation star might? Or does it have sort of a very high abundance of these heavier elements that would kind of indicate that, by this time, it's about 900 million years after the Big Bang, that most of the universe would have been pretty well enriched in these heavier elements by a lot of previous generations of stars. So it's going to be a really cool thing to look at and kind of get a sense of, what these stars look like in the very distant universe, and how these stars are, going to be, in some ways the same, in some ways different than the stars that we see in the Milky Way. So it's going to be incredibly exciting to actually dive into this Webb data for this particular star and get a sense of how this very, very early star is actually looking, and how it's going to compare to nearby stars. The other thing that's really exciting with Webb is that Webb is going to be able to break this record. So this is something that we're seeing about 900 million years after the Big Bang, but Webb is going to have the potential to see gravitationally lensed galaxies at much greater distances, and potentially very highly magnified stars within some of these lensed galaxies at these great distances. So obviously we have Webb observations to observe this star, but then there are some other programs that I'm a part of with the Webb telescope that are going to be observing other galaxy clusters that are known as strong gravitational lenses, and potentially looking for some of these even more distant galaxies that could be the home to these even more distant gravitationally lensed stars that could break this record and potentially give us some actual observations of the very first generation of stars. And we really need this gravitational lensing effect to do this kind of work. And it's very exciting that we have a bunch of data coming in from the Webb Space Telescope within the first year that's gonna give us a chance to study this one very distant star that we've already found, and give us plenty of opportunities to look for more and hopefully break this record very soon. Ideally, I would love to see this fall within the first year. That would be incredibly exciting to find ever more distant stars as we start looking through this early data from the Webb Space Telescope. So I will leave you with just a couple pretty pictures again, and just say that the future with the Webb Space Telescope is very bright. It's going to be incredibly exciting to see all of the incredible things that we find. We have some idea of what we're looking for, but Webb could reveal things that we absolutely don't expect. And I'm incredibly excited to get to work on this data going forward, and just kind of see all of the discoveries that we might make with this. So thank you for listening, and if there are any more questions, I'm happy to answer anything else.
Okay, great, Brian. Thanks. Awesome talk. I do have a question myself, and then kind of tag it on to someone else's question. I think you already kind of answered, but I want to double check. Jim Switzer asked if you'd be able to get a full spectrum on that Earendel star, and then does lensing affect the spectrum in any way?
Yeah, so I'll start with, yes, we will be getting a full spectrum from Earendel. The first cycle, we're going to use the near spec instrument, which kind of covers the more near infrared section of the spectrum. So we're going to get from about 1 micron to 5 microns, which is going to give us enough to be able to say that this is absolutely a star and not just something that we're pretty sure is a star. And then it's going to be able to give us that detail, like I was mentioning, of what type of star this is. So like an O star versus a B star or some other type. And then with future observations, we're going to use more of the mid-infrared instruments to look at longer wavelengths and try to get a more complete infrared spectrum from this. But for that first cycle, it's just going to be the near spec instrument in that more near to mid infrared range. And then as far as the second question, lensing does not affect the spectrum. So it lenses all wavelengths of light the same way, which makes it, unlike most lenses that we have on Earth. So it's a little bit different in that sense, but it doesn't change the colors. It doesn't change the relative, brightnesses of different features of the spectrum at all, which means that as long as we have a value for the magnification for an object, we can easily put together from a spectrum, what this would actually look like intrinsically. We just need to, basically divide by the magnification to get the intrinsic brightness.
Okay, great. David Easley asks, how long do you expect the lensing effect would last? Are they transitory, or is there like a certain amount of time they last?
Yeah, it kind of depends on the object that you're looking at. So with galaxies, they're not going to be changing on anything close to a human lifetime. So, in theory, as things kind of move around, you might get slight changes in the amount of magnification for a full galaxy, but realistically, it's not going to change in any appreciable way. For stars, that's not quite the same. So stars are much more compact objects. And like I was saying before with some of those previously discovered lens stars, as they move relative to the actual lens, as things kind of line up just quite right and then just not quite right, you can get these little changes in magnification that kind of give you temporary boosts in brightness, which then go back to a more long-term lower magnification. So this is usually when you have something like a star within the gravitational lens that just kind of temporarily aligns with that background star. That just boosts the magnification up a little bit, and that's what led to the original discoveries of these gravitationally lensed stars. In the case of Earendel, it's actually not going to fluctuate that much. So we did a bunch of calculations for how many stars are in the area from the lensing cluster, and when you combine that with the total magnification from the cluster, you kind of find that there are enough stars that all these little, what we call microlensing events, would sort of overlap to the point that we're going to see the brightness of the star stay within sort of a factor of 2. So it's going to stay really bright and just kind of jitter a little bit up there, but it's not going to have any drastic changes over the next decades. In theory, depending on which way the star ends up moving, it could within maybe a few decades, it could potentially drop in magnification to the point that we would no longer be able to observe it with Webb. But based on our calculations, that's not going to happen for tens to hundreds of years. So we think that it's going to be around long enough for us to get a lot more detailed observations of the star. And I think generally with these more distant objects, it kind of helps with that too. You tend to have with much more distant objects, the lensing effect doesn't change quite as rapidly and as dramatically as in some of the closer objects like the first lens stars that were discovered. Okay,
great. Our next question is from Leon Fasano. I hope I got that right. Can our small telescope see any lensed stars or galaxies, or do you know of the smallest telescope that can see something like that?
The smallest telescope that would be able to see it, I don't know off the top of my head. I would say probably most people's backyard telescopes probably wouldn't be able to see these. Although there are a few sort of giant arcs that could potentially be visible if you have a large backyard telescope. Like if you're the kind of person that builds a dome in your backyard to house your big telescope. But most people's little travel size Celestron telescope isn't going to be able to pick these out. You need a higher resolution to be able to pick out the lensed arc from the rest of the galaxy cluster. Otherwise, it's just kind of going to look like a more of a merged blob from all of the foreground objects.
Okay. Uh, Eric Clays is already asking for your return talk once you have the data from the web. Is that going to happen, you think?
Yeah, absolutely. I'd be happy to come back and share more about what we actually get with the web data.
Great. That's good to hear. So Wesco asks here, what do you expect to learn about stellar evolution or galactic evolution by observing more distant stars?
Yeah, so as far as the stars themselves, the time period that we're looking for sort of within this first billion years is a time that we expect stars and galaxies to look very different. So for the stars, for example, like I kind of mentioned, they're likely to have much fewer metals than stars that we see nearby. So you're going to have mostly fewer heavier elements like oxygen, carbon, et cetera. So that's going to be one of the big differences, and that can kind of mess with the way that stars form and evolve. This is still a very active area of research, but one thing that seems to stand out is that typically we're finding that these lower metallicity stars tend to form a larger number of very massive stars. So you'll get more of these, giant, tens to hundreds of solar mass stars, as opposed to as you get to later stellar populations, you'll get sort of the average mass of a star in the Milky Way, for example, is about the sun, the mass of the sun. In these most distant objects, it's a few people have predicted that you're more likely to get these much more massive objects. So being able to study these individual stars and then the galaxies that they live in is going to give us a better understanding of if that's actually true, if these stars are forming typically more massive stars, and then what those massive stars are actually doing, how they actually look. So once we're able to get a good spectrum of some of these distant stars, we'll be able to pick apart what is actually inside of these stars and get a better sense of how they're eventually going to end their lives and then contribute to sending more of the metals that they produce inside the stars across the rest of space. So yeah, we're definitely going to learn a bunch about how these stars are forming and evolving, and also how the galaxies that they live in are forming and evolving. And this is something that Webb was really designed to do, is give us all of this information about these most distant, earliest galaxies.
Okay, great. Wes has another question. You have to apply any sort of computational image reconstruction algorithms to form the Webb images.
Yeah, there's definitely a bunch of computation that goes into producing these images that we're seeing from Webb. The original images that we get are always a little bit rougher around the edges. So things like cosmic rays hitting the detector cause little streaks across the images. I know with Hubble, there's like dust on the mirrors in various places that we have to take multiple pointings that kind of move ever so slightly around the target that we're looking at to kind of correct for some of these things. And then we have computer codes, once we get the data actually back down to the ground, that can add these things together and kind of mitigate those issues that we see. We're going to have similar things with Webb. So we've got codes that are meant to take the raw data that we get and reduce it into this form that we're seeing right here, which kind of does those corrections for all of the weird things that you might see when you're just looking through a telescope with one quick picture. But it's people have spent a lot of time working on these, and this is something that it's going to be a bit of a learning curve as we get the first data, trying to figure out what the best practices are for actually reducing the data. But we have a lot of this set up already to actually hit the ground running once we do get these first images.
Okay. I thought I saw another question popping up, but it went away. So I'm assuming those are pretty powerful computers running that code to do that data reduction. And yeah. I think that was what the question was asking, but the question was away. I do have another one popping up here now. Oh, and apparently there is there was a gravitational lens caught by an amateur telescope, but it was very extremely tough, I guess. So the next question is, do you use something like flats and darks to help do this data reduction and clean up those images?
Yeah, definitely. So, when the telescope was on the ground, they took a bunch of flat field images and dark images to get a sense of what the detectors were doing. Through the commissioning process, they're doing more of those those tests to try to get a sense of how the detectors are still performing once they're actually up in the air and cooled down all the way. This is sort of the last stage of the commissioning is making sure that we have all of these necessary components to make sure that we know exactly how the detectors are performing before we actually start taking the science data. So this is kind of the last step that's happening right now is making sure that we're fully characterizing these detectors. But yeah, we definitely take advantage of those flat fields, dark images, trying to get a best sense of what the detectors are doing before we try to take our science data.
Great. Okay, so there's another comment here by David Easley. There's a proposed idea of using the gravitational lensing of our sun with a space telescope position far enough away for looking at exoplanets. Any ideas on this? And then would you want to work on something like that?
Yeah, it definitely sounds like a really interesting idea. Typically with the sun, the biggest problem is blocking out all of its light so you can actually see what's behind it. So it's a really cool idea, and I think it could definitely give us a good boost, especially like the question mentioned, looking for those exoplanets, things that are closer by. I think it's just a technological challenge at this point to get there. So personally, I don't know exactly what the state of that sort of idea is right now, and how feasible it is, but it definitely sounds like a really cool idea.
Okay. At the moment, that is my last question, but they always come in after I say this. And a reminder, if anybody wants to post to the email, they could also do that at questions@naperastro.org. But Brian, I think it looks like we are at the end of our questions.
All right.
Yep. So thank you very much. And Jim, if you are ready, I will turn it back over to you.
Yeah, thank you very much, Brian. Actually, Chris, you just had another question come in.
Of course.
It says thoughts on long-term exposure such as Hubble Deep Field.
Yes, there are actually, even as part of one of that program that I was mentioning that's going to look at those various galaxy clusters, that is part of a larger program that's going to get what they're calling a medium deep field. And then there's another project that's getting sort of an initial deep field within the first year of the Webb data, where they're kind of going to go a little bit deeper and get some of these longer exposures. It's tricky to do, especially in the first year, just because there's so many people who want telescope time. So trying to convince someone to give you, obviously with the larger mirror, that's gonna, even that lower observation or shorter observation is gonna give incredibly deep images that are gonna be able to show a lot more than anything Hubble could do. So and then obviously going forward, as the telescope is around more, we'll keep coming back to the same fields. That's something that astronomers like to do, is keep observing the same thing over and over again to see if it changes. And as we get more and more of those observations, we can stack those and sort of produce an ultra deep field that it's probably gonna give us a lot of really cool discoveries if we do that.
I was going to post my own question here, Jim. I just thought of one. Is Webb going to be used in the multi-band imaging of transitory objects like supernovas and stuff?
Yeah, definitely. A lot of people have applied for programs to specifically say, like, we want this much time to follow up supernovae as they're discovered. That's the thing with supernovae. You never really know when or where they're going to be. the challenge with Webb is that at any point it doesn't have the ability to look at the full sky. So if it's a supernova that Webb can't quite see at the time, then you're kind of out of luck. But it is definitely something that that people have proposed for and that people have plans for, is going after some of these supernovae, and hopefully looking for even more distant supernovae. So this was looking at these very distant supernovae is how people were able to first discover the accelerated expansion of the universe. And as we continue to look even more distant, then that's going to exactly how this acceleration is going. So it's going to be a cool thing to look at.
Okay. And one more, Jim slipped in here. How did you get into your profession, excuse me, and do you have any advice for young students interested in STEM astronomy?
Yeah, absolutely. So personally, I kind of got into this thanks to a couple of awesome high school teachers. So I went to Wheaton Warrenville South High School, which is just up the road from a lot of you, not too far away. And the two physics teachers that I had there were awesome. They really both got me interested in studying physics. And then when I went to college, I was told right off the bat that if you want to do physics, you have to start doing research over the summer. And when I first started that, I just kind of picked a few different things and did them all part-time over my first summer. And one of them was an astronomy position, and it was so much more interesting than anything else that I was working on. So that was kind of how I got into astronomy. Was just, I started doing that research and I kept going with it, and it kept being the most interesting thing that I was doing. As far as advice, if anyone is interested in astronomy and, just starting to get into it, any sort of experience that you can get, just getting your feet wet with any sort of astronomy research is incredibly valuable, just to learn exactly how astronomy is really done, and then also to get a sense of if it's actually something that you would want to pursue long term. And I'll say that most astronomers are pretty open to just getting cold emails, especially from younger students. So if you're a high school student or first or second year college student, and you have no idea what you're doing, just start reaching out to people who are doing interesting things. Ideally professors. I will say that I, as a still early career person myself, I don't really have too much of an opportunity to give someone direct research experience. But if you reach out to professors and people who just start Googling names and looking up lists of people at nearby institutions, you can find people and just start sending emails. Someone will be happy to have you come along and do a little bit of research work and kind of show you the ropes and give you a chance to start getting into it and start figuring out if astronomy is really something that you want to do long term. And then that sets you up for everything else down the road.
Okay, great. And I do believe that is finally the last question.
No, you're wrong, Chris. There was one more.
Really? Oh,
Yeah.
I missed it. Okay.
Is James Webb going to be used on transitory targets?
Oh, that was my question, Jim.
Oh, that was your question. Oh, sorry.
Yeah, so I just typed it into for recording it. So
Sorry.
So no, I'll turn it back over to you then, Jim. Thanks, Brian.
Thank you.
Thank you very much, Brian.